Today we will finish up set theory, and we will do this by looking at surveys. We will be using all of the information that we have learned so far. Before we begin with actual surveys, let's do an example. Suppose that we have the cardinality of a set A that is 5, a set B with cardinality 12, and we know that the cardinality of their intersection is 2. We could ask, what is the cardinality of their union? The easiest way to go about this is to start with a Venn diagram, and since we know that the intersection has 2 elements in it, we can just put 2 little lines in there. Now, we know that the cardinality of A is 5, but we've already accounted for 2 of those elements, which means that we can go ahead and put 3 more inside of A. We now know that the cardinality of B is 12, but we've already accounted for 2, and so I can go ahead and put 10 more in B. I can now answer the question, what is the cardinality of A union B? Well, the cardinality is the total number of elements in the union. So I have 10 from just the set in B, 2 from the intersection, and then 3 in A, which gives me a grand total of 15. This brings us to a formula that the cardinality of A union B is equal to the cardinality of A plus the cardinality of B minus the cardinality of A intersect B. We can extend this to 3 sets, but it's not quite as easy. Let's look at an example. Here's an example where we have a lot of information and we have 3 total sets. Well, we actually have 4 with the universal set, but that's not important for this yet. So what we want to do when we're presented a problem like this is to start with the smallest set that doesn't have any other regions in it. And what I mean by that is that if you look at A intersect B intersect C, well, that's the little region in between or where all 3 circles intersect. And there's no other region that intersects it. So it's sort of the smallest region you can have. Because we have 6 elements in the intersection of all 3 sets, I'm going to put a 6 right there. Now we can look at the intersection of just 2 sets, and you can see that for instance, A intersect C has 2 different regions, but we already have 1 number filled in. So if we have that A intersect C is 15, that's in the information given, and we already have 6 of the elements accounted for, that means in the other region we have a total of 9 elements. Alright, now the next little piece of information we can deal with is the cardinality of B intersect C. We know that B intersect C has 8 elements, that's in the information given. The region that would be shaded in for B intersect C already has 6 elements in it, therefore we can go ahead and put a 2 in the other little region. Just to give you an idea, if we wanted to go ahead and fill in the rest of A, we wouldn't be able to do that because what's left in A right now are 2 different regions. And so even though we know A has 24 elements and we've accounted for 15 from the 9 and the 6, we don't know how to divvy up those remaining 9 elements from the 24 minus 15. So let's go ahead and try to find the next smallest region, which is where A intersects B. We know that A intersect B has 10 elements. We've already accounted for 6, so that means I can put a 4 in the smaller little region. Okay, now let's go back and address this question. Can we now fill in the rest of A? Well, yes, and we can do that for B and C as well. Alright, let's start with B. B has a total of 24 elements, and before we write that 12 there, we've already accounted for 4 plus 6 plus 2, which is 12 of the elements. That means that there has to be 12 more in B, and we can put a 12 in the remaining region. Similarly, for C, we've already accounted for 9 plus 6 plus 2. That gives us 17 elements. but C has 26, which tells us that in that region only in C there has to be a remaining of 9. Lastly, for A, we have 24 elements, but we've already accounted for 19, which means just in A we have 5 elements. Alright, now let's deal with this universal set. The universe is everything inside of the box, and we know that there has to be a total of 50 elements inside this box. How many have we already accounted for? Well, if you count up 5 plus 9 plus 4 plus 6 plus 2 plus 12 plus 9, you will get 47. That means that there were 3 elements which we did not account for when we filled in the circles. So there are 3 elements in the outside of all of the circles. Alright, as a comment, remember to start with the smallest regions. Or if you want, you can start with the middle and work outwards. So again, sort of the intersection of 3 sets, and then you can deal with the intersection of 2 sets, and then the remaining sets. Alright, here's another example. This one is actually a survey, and this isn't any more difficult than the problem we just did, except there are words to it. But really the words don't matter. What's important is the information given to us in terms of the sets. Alright, so Scott leads a group of software engineers and investigates illegal activity on social network sites and reports the information. He finds, he has 3 sets. He has a set of members that have patterns in Twitter, Facebook, and LinkedIn. And then we have the cardinalities, meaning, for instance, we know that 13 people follow patterns on Twitter, 16 people follow patterns on Facebook, and you can continue in this fashion. But the question is, for instance, how many engineers are in total Scott's group? It would be ill-advised just to add up all these numbers because there's lots of overlap. For instance, the set T intersect F intersect L is a subset of T intersect F. So we would be overcounting, which is why when we do these patterns in these surveys, we start with the smallest regions and work outwards. But we are trying to answer this question, so what can we do? We use this information, we pull it out of the word problem, and we start in the exact same pattern as before. Alright, so we have the region of T intersect F intersect L. I've labeled the Venn diagrams appropriately, and I know that we have 5 members in all 3 sets, so I'm going to put a 5 in the middle. My next goal is to try to deal with the rest of the little islets. In other words, where 2 sets intersect. Alright, so we can do all 3 of these. For instance, we know the cardinality of T intersect F is 9, but we already had 5, so I put a 4 in the remaining region. We have the cardinality of F intersect L is 10, so I put a 5, and then the cardinality of T intersect L is 6, so I put a 1. Alright, I'm now able to use the information on the left, so the cardinality of T, F, and L, to fill in the other regions. Okay, so let's just take a look at this. We put a 3 in the remaining region of T. Let's just make sure that all of the numbers inside of T add up to 13. So we have 3 plus 4 plus 5 plus 1. That gives me a grand total of 13. It's never a bad idea to check your work as you go. Alright, so this is a little bit different than the last problem because in the last problem we were given the universal set, or the cardinality of the universal set. But that's not what we're given here. What we're given is we're given the cardinality of T complement intersect F complement intersect L complement. So what region does that represent? Alright, it actually represents the outside region. And I know this because if I were to go about coloring in the Venn diagram to find this region, I would first draw T complement. That's everything outside of T. I would then shade in F complement, which is everything outside of F, and then I would shade in L complement. Now this is pretty complicated to look at, But remember, since we're looking at the intersection, we want to look at where all three colors overlap. And when we clean this up, we see that they all overlap in the outside of those circles. So if I know the cardinality of T complement intersect F complement intersect L complement is 3, that means I need to put a 3 on the outside region. All right, so let's go back and answer this question. How many engineers are in Scott's group? Well, we're looking at adding up all of these numbers because every single number represents, well, 3 represents 3 of Scott's members. So when we add these all up, we have 3 plus 4 plus 2 plus 1 plus 5 plus 5 plus 2 plus 3. We get a grand total of 25. So our answer is going to be 25. All right, so I encourage you to go back and pause the slides when necessary as you're working out these problems on your own. We did go through them relatively quickly, but you do have that capability to pause and rewind. All right, I'll talk to you later. Bye.